As seen in the video, when the two spatulas are pushed together and pulled apart, there are lines that run in between the surfaces of the bubbles. These are called dislocations. Dislocations will start where stress is created. For example, as the spatulas are pushed together and when they're pulled apart. It will then move from one end to the other, much like a person moving on a ladder. It will also move in the opposite direction of strain until gone. The motion of dislocation is when the dislocation moves without changing the structure as it changes the shape. If two dislocations meet, they will either cancel each other out or create a new dislocation that will go in a new direction than the two previous.
Burgess vectors are a tool used to determine if a given lattice is deformed. A box of equal side lengths is drawn around the suspected flaw. If a dislocation is present, the box will not move smoothly when closed. Instead, it will overshoot the initial side of the box by some amount. This spare length is the Burgess vector.
During the deformation of a metal, a grain boundary is created when adjacent grains are oriented differently. A grain boundary acts as a barrier to dislocation motion. The first reason being that since the two planes are at different orientations, the dislocation has to change direction of motion. The second is because the atomic disorder of the grain boundary region is a disconnect from one grain to the other. This is shown in both pictures below in the curved lines. Onto high-angle and small-angle grain boundaries. The orientation of the two planes in the structure determines whether it is high angle or small angle. The areas of misorientation are at a typically higher energy than that of the rest of the structure and often contain impurities within the metal. In image 1, you can see the small angle grain boundary, and in image 2, you can see the high angle grain boundary, both represented by theta.
Dislocations frequently will interact with grain boundaries. In fact, grain boundaries are a region of the crystal structure where dislocations are likely to originate, as well as places where dislocations frequently terminate. This is due to the grain boundaries being regions at which stress will concentrate. By forming dislocations and resolving them at grain boundaries, the structure can decrease its overall energy, and as a result, dislocations are frequent along grain boundaries. We can see in the bubble model lines of dislocations marking the grain boundaries, whether obviously as visible lines of displaced bubbles or in a more subtle fashion, along shallow grain boundaries, which are often only evidenced by the presence of dislocations. As stress is applied to a crystal structure, the structure will slide along the grain boundaries before it will cause the whole formed crystals to shear and deform. As stress increases to the point that it will cause the crystals themselves to shear, cracks and dislocations will propagate to form new grain boundaries. This shifting and reshaping of the grain boundaries can be seen in the bubble raft model.
Vacancies occur when an atom is missing from the lattice. These gaps cause tension on the surrounding lattice.
An interstitial is a defect in a crystal structure, where normally an unoccupied space in the crystal structure is occupied by either an atom which is normally part of the structure but for some reason is out of place, or by an atom foreign to the crystal structure. In the instance of our bubble model, bubbles of larger or smaller size can be considered interstitials, interrupting the regular pattern of the bubbles of more uniform size.